In Monday's class, we developed this through a discussion, but summary is if a ball's rolling down an incline, then we can depict its weight vector, normal vector, and displacement vector, as well as the friction force vector. Note that the displacement vector has units of length. It isn't measured on the same scale as the weight force or frictional force vectors, all of which have units of force. Okay, vector picture of the work done by the weight then, as our typical dot product picture. Here's our weight, here's our displacement. We project the weight on the displacement, we get the parallel component of the weight, which is then multiplied by the displacement in order to get the work done by gravity. In this case, the work done by gravity is positive, since the weight is in the projection of the weight vector, the parallel component of the weight vector, meaning the same thing, is in the same direction as the displacement. Now this represents the forces and displacement on the first ramp. Remember that we're dealing with a situation where a ball is going down one ramp and up the other. Right now we're only talking about the first ramp. What about the work done by the normal force? Well, the work done by the normal force can be depicted by another vector diagram, and I didn't color the delta x vector. That would be a good thing to do. And that's actually our delta x1 vector and our force m1. Well, the normal force vector, remember the normal force is the response of the incline to the weight, to the component of the weight vector perpendicular to the incline. So the normal force vector is also, perpendicular to the incline, so the normal force vector will be perpendicular to our displacement vector. Displacement vector, of course, being along the incline. Since this vector is perpendicular to this, its projection is 0. So the work done by the normal force is 0. And then the friction force. This dot here represents the point at which the frictional force is applied, and the point at which the delta x vector originates. So we have the frictional force on the first incline. The displacement vector should also be colored. Didn't match up very well there, but hopefully you understand what I mean. And there's negative work done by the frictional force because the frictional force is in the direction exactly opposite that of the displacement. So we can get the work by the frictional force by simply multiplying the whole frictional force by the displacement. In other words, the frictional force is its own projection on the line of the motion. Okay. In this case, the weight does more work than friction because the magnitude of the projection of the weight vector is greater than the frictional force vector. In other words, this projection is bigger than this, according to this picture. It's not necessary that this actually be the case. The frictional force vector could be bigger than the component of the weight vector, in which case if the object was, or the ball was at rest, it would remain at rest. But if it was already in motion, it would continue to move, being slowed down by the net force. Net force, again, if the frictional vector is bigger than the parallel component of the weight vector, the net force on the object is going to be negative. The work done by the frictional force, the negative work done by the frictional force will be of greater magnitude than the work done by the gravitational force. Okay. And the object will lose kinetic energy since the work done is negative. Remembering that the work done by the net force is equal to the change in kinetic energy, the work kinetic energy theorem. Another observation, the change in gravitational potential energy. Now we haven't talked a whole lot about potential energy, but when the ball is here, it has the potential to accelerate down the incline, and if we release it, it does so. By virtue of its position, it can gain kinetic energy. Work can be done on it by virtue of its position. And in that case, we say that it has potential energy, the potential to gain kinetic energy, the potential to do work. So, intuitively, we're going to say that when an object decreases its altitude, when it rolls down an incline or when it falls, its potential energy is decreasing, because if the ball is further down the incline, it's going to have less potential to do work between here and the end of the incline. So the gravitational potential energy turns out is negative when the work done by gravity is positive, because here we see the work done by gravity is definitely positive, but the potential energy of the ball is decreasing. So that's kind of a paradigm example you want to keep in mind when we get to the more formal definition of potential energy. In this case, the change in gravitational potential energy is equal and opposite to the work done by gravity. I'm not sure the camera's getting that. Okay.